Hello and welcome to another episode of the Fully Charged Show podcast. This is, that is a very bad opening for what is actually a very really kind of serious and highly informative and intelligent episode. So I shouldn't do lots of silly noises and accents, not on this episode, because this was a fascinating opportunity. And I don't know if I was sort of slightly worried about it because it's so kind of inside baseball in terms of discussing battery technology, which, as you will learn by the end of this episode, I know very, very little about. You know, when you're faced with someone who knows a great deal about it. But I had an amazing conversation with a wonderful man called Dan Blondell, who lives in Vancouver, in British Columbia, in Canada. I'm just, as I said that, I was grimacing a little bit simply because it's such a beautiful city in such a wonderfully stunning part of the world where, to an uneducated European ear, it sounds like you're in America until you hear there is a very different flavour to the accent, lovely, gentle North American accent. And Canadians are fantastic. They're very different from Americans. Although, as we now know, most Americans are highly sensible and lovely, which I always knew they were. I've met so many lovely Americans, but I've never met anyone who isn't beyond perfect in Canada. I'm sure there's some nasty people in Canada. I've never met them. So Dan Blondell is definitely a nice man. He works for a company called Nano One. And Nano One they were set up about 9 or 10 years ago. Dan will explain in the podcast, but they basically have refined the process of creating more cheaper batteries that last longer, that have greater energy capacity, all those things. And they're called Nano One because the process that they use is called the Nano One process. It's a one-pot battery materials fabrication and manufacturing company. And when we heard Elon Musk discussing the new battery technology that Tesla are adopting, it was very much based on the work that Nano One have been doing for many years. So they're kind of hidden. They're not like a big flashy company like Tesla or like Rivian or the Chinese companies, NIO or BYD. He mentions BYD a lot, and what they're doing is very interesting. But they are absolutely critical to this transition, and I can only apologise for the lack of my understanding. I think that, but what I hope is that will keep the general information that Dan could tell us about a little bit more comprehensible for more people, because battery technology is weird. I mean, it's a chemical process inside a tube, and it's a difficult thing to understand. And I get the absolute basics of it, but the finite stuff about the materials that go into it, what those materials are, why they're needed, where they come from, all those things are touched on in this, I think, very fascinating episode of the Fully Charged Show podcast. So without more ado, please welcome Dan Blondell from Nano One. So I just want to thank you, Dan, for taking time to talk to us today on the Fully Charged Show podcast. I just love this is one of the good things of the lockdown. We've just gone into a big lockdown in the United Kingdom today. And one of the advantages is I actually get round to talking to people. You're in Canada. I mean, I don't know how I would have organised this at any other time. So it's a great privilege, and thank you for finding the time, because it's in mid-morning for you.
Yeah, right. Just before lunch, and
right.
And listen, I really appreciate the opportunity as well to speak to you and to get in front of your audience. So thanks very much.
Very good. Well, no, it's because when we first made contact was around the time of the Tesla battery announcement, the much heralded Tesla battery announcement, and it sort of made an impact, I think. But I think a lot of the technology behind it and the more technical side of it, people just got a bit fuzzy-brained and went, I don't know what that means, a tabless battery and all those things. But there's one topic that I think is it's worth kind of considering, which is the million-mile battery concept.
Which, interestingly enough, they didn't bring up in the
no,
in their,
it was hyped before. Yes, it was never mentioned. But I get the notion of it. It's not so much that you would have a car that would do 1 million miles. I mean, that would be quite a big challenge just mechanically. But I can understand you could have a battery that could last that long.
Yeah, look, the concept of 1 million mile battery doesn't make a lot of sense for the average consumer driver, because that's a 75-year car.
Yes.
But the concept is really underlying it all is just that it's a more durable battery, and so a more durable battery can play out in different ways, right? So for a taxi company that's got a taxi running 12 hours a day, 1 million miles makes a lot of sense. Or for anything with a heavy duty cycle like a bus, or even grid storage for renewable energy, those kinds of things kind of make a lot of sense. Yeah. For the average consumer, what really a more durable battery translates into is better warranty, so which means a cheaper battery. It could mean that the company can, or the car company can charge it more aggressively, right, because it's a more durable battery. So let's shave off 500,000 miles on that thing, and charge it 10% faster. Right,
I see. Yeah.
So that's what that durability sort of gives some flexibility to the battery designer to charge it further, charge it faster, maybe deep cycle it more, so you get a little bit more mileage out of the battery, and there are various things like that. Right. And because all of that stuff gets constrained in the battery design, and it's all built around the warranty and the liability of the battery, how long it's going to last in the car. Yeah. So a more durable battery kind of shakes out in many different ways.
Yes. So because that is the fascinating thing of our general perception of batteries, and I have actually noticed this shift in the last 10 years. So when electric cars were when the Nissan Leaf came out. So I have one of the original Nissan Leafs from 2011. The general reaction of the press is very, very negative. Very much pivoted around our then experience with laptops, phones, tablets, where the batteries just after 2 or 3 years, they're just hopeless, and you can't, the charge lasts an hour as opposed to 12. And that's what everyone thought. Oh God, after a couple of years, you'll just have to throw it away. It won't be any good. And that's been a really interesting, very slow education process. And people have understood, oh, I see, they do actually last. They last longer than my laptop or my phone, these car batteries. And I kind of know why that. I think I know what that is, which is to do with battery management, protecting it, not charging it 100% full, not draining it to 100% empty, which you would do on a laptop or a phone. I'm guessing, is that one of the reasons?
Well, actually, your laptop or phone still has a battery management system around it, and it's still controlling the state of charge in terms of how fast you're allowed to charge it, and how deeply you can charge it or discharge it. So they still have those systems built into the charging mechanism. So a car has to do that in more, obviously, quite a bit more, and govern that quite a bit more. But really, the big advantage in an automotive, it's pretty simple. It's a big battery. And it's a big battery because you want to drive it occasionally. You want to drive it a couple hundred kilometers. Yeah. But most days, you're only driving it 50. And so the duty cycle on the average automotive battery is far less than your phone. Your phone's going to get fully discharged, and your laptop's going to get fully discharged in a day. So the duty cycle's 1 day. In a car, if you take a 500 kilometer range battery and your average driving day is 50 kilometers, it's a 10-day cycle. Yeah. So it's going to. It inherently has 10 times more capability. It'll last 10 times longer than your phone battery. And it's what it is that the I guess the thing that really has driven that has been the range. Range makes for, you need to have a bigger battery, and a bigger battery just lasts longer because on average you don't need that range. You're just carried around with it.
Yeah. I mean, that's the big debate is, that we're carrying around huge batteries that, I have a car a Tesla Model 3. I drove it today for the first time in about 3 days. It's, I could have driven to Scotland in it, but I don't. strangely enough, I drive to the local store. That's actually what I do. That's what you do with them most of the time.
Yeah, and at that rate, your battery probably will last, 20, 30 years. Simply because the duty cycle is super low.
Yes. I think those are the critical things that, I want to get back to the kind of actual chemistry of the batteries, but the facts that I learnt once I started driving electric cars, talking to engineers about them, understanding the use. I'd never thought, when I had a gasoline car, I never thought, I don't use that car for 90% of it the time I own it. No, it never occurred to me. It's just like it was a car. We're used to it. And once you know that, you then go, having a car is the most ridiculous. Well, it's a massive privilege and, waste of a resource. And why isn't someone else in my car now? Why is it my car? Why isn't someone else using that car?
All that lithium and cobalt and nickel that everyone talks about in industry is like tied up in your car, sitting in the driveway for 23.5 hours a day.
Yeah.
And
yes.
So from a sustainability point of view, it's kind of in the wrong direction. What you really want is you want the steel and the rubber and the plastic and all those battery materials to be used as much as possible.
Yes.
And if it wears out in 4 years, that's not a big deal. At least
no, but it will have done much more work than it would with me having it for 30 years. Yeah.
Correct. And then it would drive the recycling industry actually much quicker as well, and sort of bring that into place. So I think ultimately the goal of car sharing, robotic taxi, and then they will need the million miles actually. But
yes, it's when it goes into that sort of area that you think about it. But so the thing is, then the battery that Tesla launched, that Elon Musk showed, the new battery cell that they're going to start manufacturing. That's an incremental improvement? I'm assuming, because this is one of the things I learned a while ago, was that the energy density of lithium-ion batteries is increasing by about 6% a year. I don't know if you agree with that or think that's accurate, but it's probably in that kind of range. Right.
The energy density is improving now. The challenge is that the chemistry, the chemicals that go into it, are kind of close to the theoretical maximum anyways. The real challenge is how can you pack more into the can?
Right. And so just quickly, so it's not close. You think there is room for an enormous amount of improvement, or a lot of improvement?
It's on the engineering side, and that's actually fundamental to what Tesla announced. They're not the first to do it, and we can get to that later. But what Tesla have done is they've thought very carefully about the design of the cell and how you might integrate that into the frame or the chassis of the vehicle.
Yeah.
And by doing that, they can eliminate a whole bunch of extra weight associated with, right now, they take a bunch of cylindrical cans, stick them all together, and they have to have the structure around it. Yeah. So what they're proposing is taking these beer can sized batteries and sticking them together, gluing them along their, the surface, make this honeycomb structure. And that honeycomb structure then provides the integrity of the frame, and then you fill those cans with all the battery materials you need. So you're using the structure of the cell to actually build out the frame, and that lowers your weight.
Right.
And that's a kind of a cell to frame or cell to chassis design that's inevitable. It's happened in fuel cells already. It's certainly happened in your phones. We can't take the batteries out of these things anymore.
No.
And it was inevitable that would happen in the vehicle space. BYD earlier this year announced the Blade cell, which is the same thing, but with LFP batteries. It's a totally different configuration.
Right.
Theirs is shaped like a ski. It's the size of a ski rather than a beer can. But it does the same thing. It essentially provides a structural integrity at the cell level that can then be ported out to the frame of the vehicle. And that reduces a tremendous amount of weight, which brings the whole energy density number up. So that's where I think that the big gains are, and that's certainly that's fundamental to what Tesla announced.
Right. I know. Just so that I understand, then, Nano One, are you working on the kind of the chemical structure of batteries? Is that what is your specialty? Because you've been going a long time. Because often people I talk to are in this space. They've started a company in the last couple of years. It's very, very new. But Nano One's been going for a considerable amount of time.
Yeah, we're 10 years at it now. We we incorporated in 2011, so that's
right.
give you a sense of where we've been at. We took the company public in 2015, and yeah, we've been going at it for quite a while now. But yes, we're focused on the chemicals that go into the battery,
right.
And so it's and particularly the cathode material. So that's one of the electrodes. The cathode is made of lithium, nickel, manganese, cobalt. Those are the raw materials that go in, and we've developed a process to assemble those atoms into the right structures that allow you to charge and discharge them.
Right. And so because this is
power.
Yeah, but this is where it gets really complicated for a non-science listener to understand. Yeah. But you're not necessarily talking about the actual manufacturing process, as in the machine that spins out the batteries and winds up the cathode and anode. You're talking about the actual materials that go into that process.
That's correct. So maybe it's worth walking you just through the supply chain. And
I think it's a very good idea. Yes.
So it starts, of course, with mining of these materials: the lithium, nickel, manganese, cobalt, iron, phosphorus, wherever it's coming from, and those raw materials will eventually go into a cathode material through a variety of steps. They'll be refining. Sometimes there's an intermediate precursor step that goes on where you mix a portion of those materials, but eventually you mix in lithium with them and you cook it in a furnace. And what happens is all of those metals start to form crystal structures, and that allows lithium to go in and out between the atoms. And that's where the charging and discharging is enabled. And it comes out as a black powder. It looks like coffee grounds.
Right.
We're not much different than that. And so we've developed technology to improve the way those materials are assembled. We're not necessarily changing the makeup of it, but we're changing how they're put together to reduce cost and improve the performance of the materials. That black powder will go to let's say a Panasonic, who will then mix it into an ink by putting these kind of binders and glue in. And sometimes it's wet and sometimes it's dry. It could be a dry process like Tesla was describing.
Right.
But they make it into an ink that gets smeared onto a piece of foil, aluminum foil. And that's the cathode. We're making the cathode material that goes onto the cathode, but the cathode is the foil and the cathode material on it.
Yeah.
And then the anode, similarly, is going to be a piece of copper foil with graphite on it, or graphite and silicone. It all gets sandwiched together with basically a porous membrane, which we call the separator, in between them, and then it gets rolled up, as you say, into a cylindrical cell or folded into a flat cell that might be in the back of your phone.
Yeah,
and that's kind of the whole supply chain, and where we fit is really just downstream of where the refiners are making these super low impurity materials. We assemble them into the cathode powder.
Because then that's thank you, because that's a reminder. I've seen that process taking place, so I should know. But obviously one of the very contentious things in that, and that's obviously a topic I'd love to discuss with you, is those materials, and some of them, as we know, are very contentious. In some ways, rightly so, but in some ways it's slightly exaggerated, and you wonder where the enthusiasm for that exaggeration comes from. But cobalt being the obvious one, that it's dug up by children in the Democratic Republic of the Congo, which, I was at a conference in Oslo a year before last, an amazing guy from Amnesty International who did that report. But he stated so clearly at that talk, it's about 0.04% of global cobalt production is mined artisanally by people, some of whom use children. So the actual amount of cobalt in the world that's actually dug up by children, this is not to deny it's happening, because obviously it's absolutely appalling, but it's so minuscule. And also the other one, because you'll know this as well, because I didn't know this until this year, cobalt is used in oil refining. It's used to remove sulfur from gasoline and diesel.
Yeah, and of course it's used to strengthen steel.
It's used to strengthen steel. Yeah.
We see it in drill bits and tool bits and stuff like that. It's for hardening steel. It's a very important sort of part of that part of that process. But listen, to answer your earlier question, where does the enthusiasm come from to kind of create this panic about cobalt?
Yeah.
It's twofold, I think. One is obviously the large automotive companies want a secure supply of cobalt.
Yeah.
And the key there is that 60% of it does come out of the Congo, and every 4 years in the Congo, they shut a mine down in order to influence elections. And the auto industry is very reluctant to have that kind of supply risk in their supply chain. So that's one of the places where there's the cobalt reduction need is coming from. And then on the cobalt enthusiasm side, you've got a bunch of junior miners who are trying to actually, they're staking their ground, and they're trying to make a case for more cobalt mining outside of the Congo.
Right.
So the junior mining and the cobalt exploration industry drives a lot of that as well. So you've got both of those things, I think, influencing the narrative that we hear out there.
Yeah.
Certainly the child mining, that stuff's terrible, and we have to do our very best to fix that. But really, the overarching things are actually, I think, more to do with the global supply of cobalt coming from one, largely one place.
And one fairly politically unstable place as well, which is a very unfortunate turn of events. I mean, is it the case they actually are sitting on 60% of as what we know of the global proportion of cobalt on the planet? I mean, is that the case?
From a production point of view, I don't know the sort of geological content. I mean, there's plenty of cobalt around the world. Some of it's just harder to extract.
Yeah.
So I think the commercially extractable material, 60% of it does come out of the cobalt, out of the Congo right now.
But are we seeing though a reduction in the amount of cobalt in the mixture that you produce? Has that gone down in the last 10 years? For sure. Right.
So we see we have seen a move from, let's say, this is entirely cobalt in your cell phone. Right?
Yes.
It's a lithium cobalt oxide battery. It's cobalt on one side, graphite on the other, and lithium shuttling between them.
Yeah. So the percentage of cobalt in a phone battery is way higher than in a car battery.
That's correct, and that's because it's actually probably the most energy dense of all the cathode materials.
Yeah.
So and all what Apple and Samsung and LG care about is thin. They just want thin.
Yeah.
Right? Thin is what sells, and that doesn't quite cut it at the automotive level, and it doesn't scale. So what there has been is an effort to replace that cobalt, and initially it was with the nickel and manganese in equal proportions, and then as we've seen more and more of a push towards higher and higher nickel content, removing more and more cobalt. But the downside is that cobalt helps stabilize nickel. So the more you take the cobalt out, the more the nickel becomes unstable, the more likely it is to sort of decay over time, and so you get a less stable material.
Right.
And that takes us all the way back to the million-mile battery thing. Is that it's very hard to make that million-mile battery from a nickel-based product or a cobalt-based product because of the inherent instabilities in the material. So finding ways to do that are really what we're doing, and what sort of many other people are doing in the world right now, is trying to find a way to, how do you get rid of the cobalt, replace it with something else to make it stable. Yeah.
But then also, I mean, I don't know, I actually have no idea where nickel comes from. Iron I know about. I've been in a big iron ore quarry, so I know where iron comes from. It comes from rocks that have got iron in them. But nickel, I don't even know what nickel is. I'm that stupid.
Well, so nickel as well largely comes from oreless, and I'm not on the mining side, so I don't want to go too deep on this. But the nickel is the nickel miners are certainly way larger than, let's say, the cobalt miners, et cetera.
Right.
Cobalt and nickel actually also tend to come out of copper mining as well. So often there's they're byproducts or they're part of the mix. But you've got very large, Canadian, Brazilian, Australian, Russian nickel producers, and these are extremely large mines. And of course, the majority of that product is going into stainless steel. Right.
That is interesting, isn't it? Because we never think of that. When you have, I haven't seen people demonstrating about how unethical stainless steel is.
Yeah, and nickel also comes out of the ground in various forms, and the nickel that typically goes into steels is what they would call like a pig nickel or a class 2 nickel. Again, it's not my area of expertise. But the stuff that has to go to a battery is an entirely different thing. So it has to be refined and made much more, have far fewer impurities in it, because you just can't tolerate those impurities in a battery.
Right. So that is interesting. So the thing is that I don't want to go on about Mr. Musk too much, but what he did talk about nickel, and ethical nickel. But what your drive is to tell me what your drive is, but it seems to be that you're driving towards manufacturing processes that reduce costs. So then it's not that you're using. This is a very badly put together question. Please forgive me, but you're not suddenly just using, I don't know, wool and recycled plastic, but you're trying to work out ways to maximize the efficacy of the materials that you're using.
Yeah. So we're still making a nickel, cobalt, manganese based cathode material. We're making a variety of other ones as well. A lithium, an iron and phosphate based lithium-ion battery material, as well as one that has no cobalt in it. So We've got various flavors of materials that we can make. We have basically it's a manufacturing platform. We can put different ingredients in it, and we can get a different product out. But essentially, the platform allows us to make any of the above. The key thing, and this actually speaks to what was announced at Tesla Battery Day, is that you have to understand all the steps that these materials go through. So nickel gets mined out as an ore. They usually get dissolved, let's say, in sulfuric acid, and then they get shipped to the cathode guys, typically in the form of a sulfate. It's a salt. It's nickel sulfate. And it's about 20% nickel, and the rest is water and sulfate. And that gets shipped around the world. And the first thing that happens when it gets to a cathode, guys, they mix it with the cobalt nickel, and all the sulfate gets dropped out and goes to waste. Right. So it's kind of a needless part of the supply chain.
Yeah.
And the sulfate waste is 5 times as much as the product that you make.
Wow.
So it just generates this huge amount of waste, and it's really not needed. It's better left at the refiner, where they can recycle it and reuse it for more, product manufacturing.
Right.
So what we've designed is a process that allows us to get away from the sulfate completely. So we we can go from other forms of nickel, manganese, and cobalt. We can go directly from a metal, from metallic powder.
Right.
And that eliminates the sulfate waste and the cost of making the sulfate. Yeah. And all the associated complexity, and so it makes it's easier to permit. It's got that whole sort of environmentally sustainable component to it that's becoming increasingly important, not just to the miners, but also to the car companies. They need to have that kind of green stamp on it, of course, and it's extremely important. But also it helps reduce cost, because it costs money to convert it into a sulfate, and then it costs money to take the sulfate out.
That is crazy. That it isn't necessarily how you dig it up. It isn't a sulfate when you dig it up, but it's been turned into a sulfate and then transported.
Well, it might come. It comes as a sulfide sometimes, it's this rock, and it doesn't really have that much nickel in it. It might have 1 or 2% nickel in it. So you grind it up, and dissolve it in sulfuric acid, and you run it through all these test things, and actually, and you extract that 2% nickel, and it can come in different forms, but it's senseless to be shipping that the waste around the world just to end up in a landfill, or maybe it has to be turned into soap or something else. But at the end of the day, it all is to us. We see it as a needless part of in the supply chain, a needless cost and needless waste, and so our process can help sort of address that. And Elon Musk when he announced this stuff at Tesla Battery played completely into our court, because it really speaks to what we're already trying to do, and we're on record as trying to do. So
because that is I suppose the two key things then that are you're clearly thinking about. One is cost, which is the obvious one, and I mean that it is that same trajectory, and I'm just wondering how much further it can go. But in the time that I've been mildly obsessed with this topic, I've seen the price of batteries really drop very noticeably. I mean, you can really see the kind of manufacturing cost price of batteries, not necessarily of the finished packs. I mean, and do you see that still dropping more? I mean, in a way like solar panels, which when I first had solar panels on the roof of the building I'm in now, it cost the equivalent of about $20,000. And I had them replaced 2 years ago. I've still got the old ones. They're in the garden. The new ones on the roof are way more efficient. They produce much more electricity, and they cost about $4,000. I'm talking it's about £3,000 UK pounds. So a massive price drop, really noticeable, and more panels. I mean, I actually got more panels on the roof for less money, and they produce twice the electricity. So our batteries doing the same. On the same
the scale of manufacturing is a big part of it, and as these mega factories go to gigafactories, and maybe they go to the terafactories, all of that helps drive down costs. But the particularly for the vehicle, I think that the integration of the cell into the frame of the vehicle that's a big driver. But and then it allows some very interesting things to happen, and. So it changes the battery management system, the control system, how they take heat away from the battery. Yeah. All of that has to be kind of thought into the process. And if you can drive down the cost of all of that overhead, then the whole battery pack itself becomes much cheaper. Right. But at the core of it all, of course, is the materials and
the materials in it. Yeah.
Is the materials going in? The cathode is anywhere between a quarter to half the price of the cell. Just the powder itself. That's
right. Yeah. Okay.
So it plays a big component. So if all of a sudden we can change the raw materials going into the cathode, then that can have a fairly major influence on the overall cost of the cell as well. Yeah. And then, on the other flip side, we're also trying to work on performance. And this speaks to the whole million-mile battery thing you talked about before. Yeah. If you can put the protective coatings on these materials, prevent the materials from degrading, as you charge and discharge these batteries, the materials inside are literally swelling and contracting.
Right. And they are. I mean, because I always find that amazing, because they are contained in a sort of a metal tube. But they are actually getting bigger and smaller as you charge and discharge them.
Yeah, but it's moving from one side to the other. So one side gets bigger, the other side gets smaller, and so
that helps the understanding a great deal. Thank you for that.
There's a little bit of trade-off, but it still causes local stress, and they break apart. And when they break apart, if you have a protective coating on there, that breaks apart, and then you get side reactions that cause the battery to decay faster than intended. Right. So we found a way to to coat the individual elements, the individual crystals, and that's the core to our technologies. Wow. Is by coating the individual crystals. Even if the whole thing breaks apart, each little crystal is already coated, so you don't it won't see the kind of damage that a larger particle will have when it falls apart.
Right, and so therefore the battery has a longer life because of that.
Yeah. So we've got some internal data that shows roughly we're seeing a 4 times improvement in durability by being able to coat those individual crystals. Yeah. It's a big part of course the value proposition. There's a cost side of it, but really you have to be also sort of pushing the durability, which allows all these other things as we talked about earlier. It allows faster charging. It allows deep recycling. It allows possibly a cheaper warranty and an overall cheaper battery, or a smaller battery for that matter, that can withstand more duty cycles.
Yes, because that is the thing, is the hardest thing to communicate to people who haven't spent time with an electric car, for instance, is the thousands of advantages that you have with an electric car, all with I have the lights and everything that is operating here now is all run from batteries in my garage. I mean,
you are all in, aren't you?
Yeah, I've gone all in.
I love it.
So, today was a very unusual November day for the UK. It was very sunny. So I've actually had about 14 kilowatt hours of solar that went into the batteries, and that's what I'm using now. And I haven't had to spend any money on grid power today, which is unusual this time of year. I will admit that for solar skeptics.
Right.
From now until about the end of March is you get very little, but you still get some. But that's the thing about the impact I think that batteries are having on our lives is incalculable. We can't see it yet. It's too early in the process, but the giga battery or whatever the hell it was that Tesla put in South Australia. It's because I have friends that live there and that have information about what's happened there. I mean, that's making money.
Yeah.
And a lot of people who do investing in things like, grids and generation have seen, that makes money. Oh, I see. You buy the electricity. Oh, you get the electricity free from a wind farm that's already there, and then you sell it when it's really expensive, and it's making money already. I mean, those things are changing the way we produce and consume, and so it's absolutely vital. What you're doing means that if I have batteries in my house, they can charge more, deplete more, and last longer. Is a very critically important aspect.
Yeah, and do it safely, of course.
Yes.
In your house, it's an entirely different thing than a two-wheeled motorbike, right? It's in your basement, and you have a wood frame house, and the last thing you want is any kind of risk on the battery, right?
Yeah. So. Now, I do sometimes lie in bed at night just before I go to sleep, going, I hope it's all okay, because we actually live unusually in the UK, we live in a wooden house. So we've got the worst of all options, really. What I guess then the thing is, in the future, do you see? Yeah, I mean that's what I was trying to say. I mean, do you see battery costs going? This is the figures I've had: sub $100 per kilowatt hour manufacturing cost. I mean, is that plausible?
Totally possible, and I think, and there's a variety of different even chemistries that will kind of go there. So not only these high nickel ones, but the ones that are cobalt free, like the lithium iron phosphate, which is really geared towards heavy duty cycle, high durability applications.
Right.
So that would be the grid storage type of applications, and that's where we're seeing a lot of these big industrial batteries going. The input materials are, other than lithium, you've got iron and phosphorus, which are relatively cheap.
Yeah.
It is probably the cheapest, safest, longest lasting battery in the world. And traditionally it hasn't had energy density for long range vehicles. But now that BYD is designing it right into the frame of the vehicle, they're shooting for 500-600 kilometer range. So to me, I see the costs coming flying down, actually. Right. Particularly in cars where if you can design it directly into the frame, then the cost, the overall cost impact on the car is very, very good.
Right. So, I mean, that's going to be the critical thing. There's a whole other discussion about existing manufacturers, legacy manufacturers, maybe possibly artificially keeping the price of new electric vehicles slightly higher than they might need to be, simply because they've got a huge amount of combustion vehicles. That's their industry. That's what they've built up in the last 100 years. In order to sell those, you want expensive electric cars. There's a lot of dubious, but with some grounding, conspiracy theories around that area. But because that's always the excuse. They are more expensive because the batteries cost so much. And you go, well, 10 years ago they did. Now less so.
It's Tesla doesn't have that problem because
Tesla doesn't have it. None of the new companies have it. Yeah.
But GM and Ford and other companies have the problem of having a relatively profitable, certainly in North America, light vehicles and vans, like trucks and vans, and it's an incredibly profitable market. So I don't think there's any conspiracy. That's just where their profit margins are high. Yes. So they're careful about the ramp up because they don't want to sewer their design. Volkswagen's the exception. They've gone whole hog into changing it, but we're kind of forced there. But I think we'll see everyone else moving there. It's the comfort level. It's going to have to do with their profit margins. How they move things forward. What comes out of COVID. Over the next last. Yeah. So how is that going to impact the bottom line of these car companies, and what's going to be their reaction when they come out with their annual report next year? How are they going to react to the bottom line? It'll be very interesting to watch, and I think it will all move towards electric vehicles because
without doubt. Yeah.
I mean, I drive an electric vehicle as well. I love it. It's transformational.
Yeah.
It's so amazing to be there and driving it. And I've heard all the same things you have about, car's got to have a grumbling noise or whatever.
Oh, yeah, all that stuff, yeah.
But really, once you get in, when I'm driving, you go, oh, well, this makes a lot of sense. There's no muffler to fall off the thing. Yeah. There's no oil to change.
Yeah, yeah. No, that whole side of it is very different. But then, okay, so the other question then is which I assume you're not directly involved in, but maybe have considered or discussed, is the recycling process. So we made a show earlier last year about a company in Germany that is recycling. Basically, they've got no batteries to recycle because they're not wearing out. That's one of the critical things. But what they're doing at the moment to test their systems is recycling batteries that are used in, I think it's BMW, Audi, Volkswagen, when they crash cars, safety tests. They'll take those batteries and break them down and recycle them and extract the materials to see how that process works. So they've got a fairly limited supply. But they were, from what I remember of the translation, slightly disappointed that they're only getting 94% of the materials that are in the battery's pack, not just the materials in the cells, the whole pack. They can only recycle 94%, which I thought sounds pretty good, but they reckon they can get to 96. They're very German about it, but.
Well, it's a good start. I mean, the lead acid batteries are 99.9% recycled, so they get everything. So that's the goal. But they've been around for over 100 years. Yeah. So it's no wonder. So that is the goal. A good deal of the battery recycling that's happening right now is actually happening from the waste stream from the manufacturers. So these will be all the stuff that's off spec and it's not quite assembled into a battery. That's going to recycling streams already.
Ah, right.
So the foils, let's say the foils with cathode material pertaining to us, because that is the most expensive component. All the offcuts and all the waste and all that stuff is going into bins and being recycled.
Right.
Once you roll it into a battery and soak it in electrolyte and put it into a pack, of course it's got to be decompiled, deconstructed.
Yeah.
And then bashed apart, and then you've got to separate all that black powder off the foil, which they call black mass, and then you've got to decompile the black mass to get right back to sort of the nickel, cobalt,
to separate all the different items.
Yeah, and then effectively, once you've got that kind of black mass, you're essentially it's a mining process at that point. So you're going to just mine that black powder. You're going to mine the raw materials back out of it, and then convert them back into another cathode material. You can't really use them as a black mass because you don't know how much lithium's in them, and the structures are gone by then. So,
but it does sound like you can extract them fairly, so that the final selection of materials is quite pure. Because you'd think if it's a black mass that's been printed onto a piece of foil, wound up, used as a battery for, I don't know, it could be 20 years now, 25 years. And then you try and extract that. It's quite mind-boggling to think that is possible. But I mean,
and there, I know some companies that are doing it very effectively and building a business out of it. And there's there's obviously some tricks to it. And there's a big safety element. You're dealing with something that's energized.
Right.
So you have to take it apart without it shorting out and catching fire and all kinds of stuff. And so there's obviously some tricks to the trade there. And then of course you're trying to do it in as environmentally friendly a way as possible to have as much yield as possible. So
Well, let's quickly talk about Jeff Dahn. I don't know if that's how I pronounce his name. I think it is, isn't it? Jeff Dahn. Because I can't quite work out. He used to be at Tesla. I remember hearing his name. So he worked at Tesla, and now did he not? Oh, maybe I've got that wrong.
No.
So you correct me.
So Jeff Dahn is a professor at Dalhousie University, and he runs probably one of the world's sort of top laboratories and has done so for quite some time. Actually, he hails from this side of Canada, from Vancouver. He did his postdoc PhD at UBC and SFU, and he was one of the early guys working at a company called Moly Energy, which is one of the very first commercial lithium-ion batteries kind of here in Vancouver. But then he eventually went to Dalhousie and has been doing research in batteries for a very long time. He's got a really large team. He had a 5-year contract with 3M developing intellectual property and patents and papers for them until about 4 years ago, and then he signed a contract with Tesla. So he is Tesla's, he's in charge of Tesla's battery research on the chemistry side of things.
Right.
Largely focused on electrolytes. So that would be that's the liquid that connects everything inside the lithium-ion battery. And his focus is on trying to improve the stability of the battery by making a better electrolyte.
Right. So that's hence the confusion then, because I think I've just connected his name with Tesla because it is connected with Tesla, but he doesn't actually work for them. I didn't realize the full.
Yeah. So he's got some kind of a research contract with them, and he's been given a position there in the last year. I think I can't quite remember, but it's head of technology development for lithium-ion battery materials or something like that.
So the notion of the single crystal, that is basically what you've been explaining.
Yes.
The idea of single crystal is what you've been developing, and you've explained it already. It now makes sense because I've heard all these terms. And now I realize that's what you've just explained to us. Yeah.
So what Jeff Dahn did with it, so he coined the term this million-mile battery,
that comes from him, right?
That comes from his research. So he put a paper out about just over a year ago, where he had spent 3 years testing a whole bunch of different electrolytes under a bunch of different conditions, in a battery that was comprised of a graphite electrode, anode, and a cathode made out of a single, what's called a single crystal cathode. So this would be instead of it being a composite spherical particle with a whole bunch of crystals in it, it's just one big crystal instead of having a whole bunch of crystals glommed together.
Right.
And actually it's made by a company in China. It's not his. This isn't his technology at all. And he had them put it onto foils and put it into a dry battery. And then he has 100,000 of these batteries, and he just puts a bunch of liquid electrolytes in them, seals them up, and tests them under different conditions.
Right.
And he was able to find a pair, an electrolyte or a few electrolytes with these single crystal cathodes that ran out to 4,000 cycles, which gives you a million-mile battery.
Yeah.
And so again, that kind of played quite well into our hands because we have a way of making these single crystal cathodes. It's actually quite economically viable.
Right.
The stuff that's been made in China isn't really economically viable. There's all kinds of challenges with scaling it up. Works fine for research. Yeah. But it doesn't really play out in sort of commercial terms. Yeah. And our technology inherently makes these single crystals with a coating around them to protect them from the surrounding electrolyte.
Right.
And so that's the work he did, the research paper he did is fantastic. It's just a superb paper, and it sets the bar really high. This is where we can, we should aspire to have a battery that lasts this long. However, there are many commercial obstacles to get there. Yeah. And so that it just kind of plays into what we're doing as well.
I mean, it is such an exciting area. This is what I think there's two bits of technology and technological development that I find absolutely fascinating. I've done a few talks for the engineers that run the national grid in the UK.
Yes.
And the first one I went to, I said, I think if I'd come to this 20 years ago, it wasn't just the national grid they were running. It was power companies, solar companies, wind farms, all that stuff. Half the audience were women. That's one thing to point out, that's the shift in the interest in that. Because I said, if I'd come here 20 years ago, it would have been really boring. There'd have been people who import coal from Poland. They burn it in a power station. It goes down a wire and you switch it on and you plug. And this is the most explosively complex new systems of smart grids and software running stuff and batteries and renewables, all that, really big challenge. But in the same, 40 years ago, you could be a lead acid battery manufacturer. Not that exciting. And the applications for lead acid batteries, we used them all. They were in use and they're still useful now. I mean, I was actually in an electric digger yesterday that was powered by lead acid batteries. Perfect for it because they wanted the weight. They wanted big, heavy batteries. It's a big, heavy machine. It needs it, and it works. Yeah. It's a fantastic thing. But now it's such an exciting area. There's so many possibilities and so many applications for the stuff you're doing. And I would imagine in the next 5 years, there's new materials coming into the battery universe that that there's certainly research going on in this country into carbon batteries and lots of other materials going into it, which who knows which ones might work. I don't know. I mean, are you doing anything in that area of sort of future?
No, for sure. So I mean, lithium-ion batteries are here to stay. And there's going to be various forms of them, whether they are in the form of a solid-state battery or a high-voltage next-generation battery, or in the form of of slightly different chemistries. I think they're here to stay. I mean, the manufacturing investment, the cost reductions are going to be very hard to beat. Any sort of incumbent battery technologies have to be able to, they're going to be playing against 30, 40 years of investment in manufacturing cost reductions. And that's the big challenge. So, and lithium is essentially, it's the lightest metal on the periodic table. And it's the smallest atom you can move around realistically. So it's actually the easiest one to stuff in and out of the either side of the battery. So from a physics and from a manufacturing point of view, I believe it is here to stay. Yeah. Some of the technology that we're working on that is very exciting is a cobalt-free high voltage cathode material. Right. That can be used. We've just proven it can be used in a conventional battery at high voltage without sort of catastrophic gassing issues, because these things will tend to, at high voltage, the electrolytes tend to sort of cause puffing out of the battery, and then it just doesn't work anymore. And we we demonstrated a battery system going out to 1,000 cycles. So like Jeff Dahn, we found an electrolyte that works with our high voltage material that is pushing it out to 1,000 cycles, which for this particular material is phenomenal. I mean, you're lucky if you can get it past 50 cycles most times. So so
1,000 is a big jump. Yeah.
1,000 is a really big jump, and it demonstrates a battery system that can run a full volt higher. So a typical lithium-ion battery is running at 3.2 or 3.7 volts nominally, maybe 4 volts. This is running at 4.7 volts. Right. So that means you don't have to have as many cells sort of in a battery pack.
Right. Yep. Got it. Okay.
And it means that you can put them in a slightly different combination of in series and parallel to make up the larger battery packs, and that has a whole bunch of sort of economics that associate with it. Right. It means there's less heat buildup when you run at a higher voltage, so it's more efficient. It can charge faster, so it's a much faster charging material. But all of that has to be enabled within a battery cell system that can operate at that kind of voltage, and we have a very exciting bit of technology on that front. So we're very optimistic about it. And it could play a role in solid state batteries, but can also play a role in just a more conventional liquid electrolyte. Right.
Dan, I want to thank you, because I don't want to take up too much of it. I need you to get back to developing new battery materials. I don't want to hold up production, but it has been amazing talking to you. I just want you to forgive me for being quite thick about it, particularly because I have actually had a lot of this stuff explained to me in the past, and I'm afraid that's the difference between myself and proper scientists and engineers like you. I can hear it, I can understand it, but then it goes out the other side. I don't retain the information.
Well, I hope I kept it to a level that everyone can walk away with and understand.
You did. No, really, really good. No, thank you very much. And that's good luck to you. And I hope that there's it sounds like there's a fairly positive future for Nano One. And I'm very, very jealous of where you live and work, because I have been there and it is amazing. Yeah, you live in a lovely part of the world. Yeah, and just south of you, there's a country that's going through a little bit of it's an interesting period of history.
That's a very gentle way of putting it.
Well, yes, the rest of the world. I see a thing I just checked the other day. I just needed to know, because the sheer volume of news that we get from the United States in this country, and then you check what the percentage of the global population is. It's 4.2% of the global population is the United States. As in, it's not that big. It's quite a small percentage.
I would say we are inundated by the news as well.
Probably I'm sure. Yeah,
even more so. Proximity.
I guess so. Yeah. Yeah. But
listen, it is certainly very exciting what we've got going, and
yeah,
I
absolutely.
I really appreciate you giving me a chance to walk you through some of it and talk more generally about the industry. It's certainly very exciting where it's going.
No, it is very, very exciting. Well, thanks, Dan. It's really good to talk to you, and maybe one day we'll get to come visit. That's in mind.
Well, and ditto. I mean, I love coming to the UK as well. So
you'd be very welcome. Just drop by if you're in an electric car and come charge it at my place. I've got loads of chargers.
Okay, it's a deal.
All right. Thank you very much. Well, I really hope you enjoyed that as much as I did. It was an amazing conversation. I was desperately... he only had a limited time, and we went over that time, of course, which is embarrassing, but not by too much, and he seemed very happy at the end, so that was good. I'm glad I didn't upset him too much, because I'd really, really love to talk to Dan again, or possibly even go and visit them, because, I mean, their technology is absolutely extraordinary and really critical to what we talk about on the Fully Charged Show. That's all, really. All the notes and links, the links to the Nano One's website, which is very full of information, are in the show notes for this episode, as are the links to our webpage, fullycharged.show, and if you're interested, and why would you be? You don't have to be at all. The links to our Patreon page, which is really the primary source of what keeps us going at the moment. And if you don't know if you've come across this podcast out of the blue, and we have heard this has happened, people have found this podcast, don't know anything about the Fully Charged Show on YouTube. We have been doing a video show on YouTube for the last 10 years. There are now hundreds and hundreds of episodes about electric cars, bikes, vans, trucks, planes, boats, and home energy systems and solar PV and the breakthroughs in renewable energy and battery storage on a grid level, offshore wind. All that stuff is covered by the Fully Charged Show. So if you haven't heard of it, go and have a look at youtube.com/fullychargedshow. And that's it. As always, if you have been, thank you for listening.